Now here we will look at Kirchoff's first law and second law, the two laws to help with the calculation of circuits. Okay, now before this, we learn about Ohm's law, right? Just to give you an idea of why do we need to use this, okay? So we will learn about Ohm's law, VIR, and what is the main use of Ohm's law? To calculate voltage, current, and resistance, right? For a simple circuit. So the circuit has to be simple, like you have one power supply, you have like a series or a parallel arrangement. You can calculate the current, the voltage using simple formula, Ohm's law. Okay. Now, what if we are given a very complex circuit? Now, what do I mean by a complex circuit? A complex circuit is the one that you see where there are many batteries in it. And then there are many batteries with different kind of, all the positive terminal kind of mixed up a bit. For example, like I put a battery here, I put a resistor, I put another battery like this. Maybe here I put another battery like that. Okay, so this is an example of a complex circuit. Now, what if I extend a little bit more? I can extend here, I put one more here, resistor, another battery here, like this. And I branched out from here also, like that. And I add one more battery, add one more resistance. Okay, it can be in many forms. So this is an example of a complex circuit. So when you have a complex circuit, you cannot use Ohm's law. Okay, Ohm's law cannot use to calculate the current in a complex circuit. So that's why we have the Kirchoff's law. Okay, so what is the main use of Kirchoff's law? For us to calculate current. Okay, the main thing is the current, because once we have current, we can get the potential difference. So allow us to calculate current through component in the circuit. Let's say if my complex circuit, we have like a bulb here. I want to know what is the current flowing through the bulb. Okay, and maybe I have another device here. I want to know what is the current flowing through here, flowing through here. That cannot be done by Ohm's law. It has to be done by Kirchoff's law. Okay, so just to give you an idea of what is it and why do we need it, because in the reality, in the actual case, you are dealing with very complicated circuits. Okay, in real life. Okay, now let's go into the first law. What does it say? Before we talk about the first law, let's understand a few things, a few components that we need to know to use the law. First is, what is junction, what is branch, and what is loop? Very simple. A junction is a point where there are at least 3 wires connecting. If you look at the circuit on the right here, a point where there are at least 3 wires. So I would mark this point, I'll call it point A. This is junction A, okay? It needs to be at least 3 wires. Is this a junction up here? This is not a junction, because you got only 2 wires, right? So this is, we call it just a turning point. It's not a junction. Another junction would be over here, point B. Okay, so that is a junction. Now, what about a branch? A branch, we look here, a continuous path from one junction to the next junction. Okay, so between these 2 junctions, A, B, there are 3 ways that you can go from A to B. You go above, you go straight line, or you go below. Okay, so there are 3 paths between junction A, B. So we say 3 branches. Okay, so the first branch is going up from here, second branch, middle, and then the third branch is from here to here. So a branch is a path between 2 points. Okay, now, and then it says here, in any one branch, the value of the current do not change. Okay, that means in any one branch, the current will be the same. Current in the first branch here, let's say I1. It's the same over here. I can label here I1, and crossing this resistor is also I1. This is also I1. But for the current in this middle branch, it could be different. Okay, it cannot be the same here. Sometimes it is the same, but the way we label it, we have to label differently because it is on another branch. Okay, so let's say I put I2, and here I put I3. Okay, now you get a point. Current in one branch is the same. Okay, then we come to loop. Loop is a combination of branches, one or more branches. And it is a continuous path starting and ending at the same point. Okay, let's say you start from one point. You pick any point that you like. Okay, let's say I start from point A. I go up, I go clockwise. Okay, so go up, come back like that. Until here. Okay, let me label this so they can see clearly. Let's say this is A, this is B. This one we put E1, R1, R2, E2, and R3. Okay, so loop 1, I can write A to E1, to R1, to B, to R2, and back to A. So that is the first loop. Okay, this is the first loop. We are going clockwise loop. Remember, loop always, you start at one point, you always come back to the same point. It has to be a closed circuit to form one loop. Now, how many branches does this loop contain? You're going from here back to this here, right? So there are two branches. First branch is up here. This is the first branch. This one. And then the second branch is the middle one. Okay, so a loop at minimum consists of, okay, one or two, usually two branches. And then other than this two loop, is there any other loop that we can find? Yes, we can go down, right? We can go down. So A, we go to E2, R3, B, and then goes to R2, back to A. So I can go this direction. It is then anti-clockwise. That is another loop. Okay. Is there any other loop that we can find from here? Yes, right. So I can start at the point here. Let's call it point C. I go to the outer circuit. So C goes to A, E1, R1, B, R3, E2, and back to C. So how many loops are there in our circuit? 3 loops. Okay, this one, and the outer one, the bigger one, the macro one. Okay, so these are the definition for junction, branch, and loop of a circuit. Okay, now then we come to Kirchoff's first law. What does the first law says? The first law says it is a junction law. It applies at junction. So it applies at point A and point B. It says that at any junction, the algebraic sum of all the currents is 0. Okay, what does it mean when I say algebraic sum? That means the plus minus, we add it together. Okay, you add it. If you got plus or minus, you add it, and then it becomes 0, the algebraic sum. In other words, to put it simply, I can say that the current entering the junction is going to be the same or equal to the current leaving the junction. That is what the first law is saying. Okay, current entering equals to current leaving. So let's say here we got I1, I2, and I3. Applying Kirchoff's first law at junction A, we can derive an equation. Okay, a very simple equation. I just write current entering. What current is entering this junction? You look for the current that is pointing towards the junction. So I1 and I2 is entering the junction. What is the current coming out of the junction, leaving the junction? That is I3, right? So I1 plus I2 equals to I3. That's it. Okay, so same here. I can label the same on the other junction, junction B. I3 here, split. This is I1. Why is this I1? Because it is the same branch, right? So it has to be the same current as this one. So here's I1. Down here is I2. Okay, so you write an expression on junction B, still the same as this expression here. So current entering equals to current leaving. That is the first rule. Okay, now another example would be if I do it like this. Let me erase this, get some space. Okay, here we got 4 wires and a junction. +5, -3, like that. Okay, let me change this. 5 ampere, 3 ampere, and this is 4 ampere. This is 6 ampere. Okay, so again, we have a junction. Current entering the junction. Which two current are entering the junction? 5 ampere and 4 ampere entering. Okay, pointing towards. Sometimes in your book, they put a sign, right? They put a sign, current approaching the junction, they put a positive sign. And current leaving the junction, they put a negative sign like that, negative, negative. So when I add up everything, I take the algebraic sum, 5 ampere plus 4 ampere minus 6 ampere minus 3 ampere equals to 0. Okay, so algebraic sum equals to 0. So current coming in, total got 9. Current leaving, total is also 9. So the first law, it follows the conservation of charges. Because what is current? Current is the flow of charge, right? So conservation of charges means how many charge go in, same as how many charge come out. You cannot have extra charges come out. You cannot have less charges come out. So it has to be equal. Okay, that is the first one. Now, I give you 1 minute. Whatever that you want to take down, you take down, and then we go to the next slide. Okay, if you look at one example down here, we box this. Identify the current in the wires. Okay, 2 ampere come in, 3 ampere also joining in, entering the junction. So how much you have here? 2 plus 3, you have 5 ampere. Okay, so 5 ampere here. How many going out? 1 ampere going out. Then you have 4 ampere. And then after this junction, 2 ampere entering, 4 ampere entering, add up, 6 ampere coming out. Okay, and then you have the next junction, 6 ampere entering, 3 ampere coming out, The other one also 3 ampere, like that. So purely using the first one, you can find out the current. Now we go to the second one. The second one is much more important. That is the loop law. Okay, now let me go to the next page. Okay, quick one. If you want to capture, then you capture. Okay, now Kirchoff's second law, loop law, is also, you call it the voltage law. Now, what does it say? It says that in any loop of an electric circuit, the sum of the potential difference across different element is 0. Now, what do I mean by element over here? Element, it can be any electrical component. It can be a capacitor, it can be a resistor, a cell, an inductor, okay, anything, any electrical component. So the loop law says that in any one loop, the sum of the potential difference is 0. How do you get the sum of potential difference 0? That means there are some component is going to have negative potential difference. That's how you get 0. Some component is going to have positive potential difference. Some component is going to have negative potential difference. So when we add it up, we get a 0. Now, let me show you what do we mean by this second law here. So let's say we use the same circuit, okay, E1, R1, R2, R3, and E2. Let's pick one loop, okay, in any one loop. So we take A, B. Loop 1, I take A to E1 to R1, B, R2. So this one here. If I add up the potential difference of every single component, that means the potential difference of E1, R1, and R2, then I'm going to get 0. Okay? Before you do the Kirchoff's second law, you always want to do the first law. That means you need to label the current first. Remember, before you start doing any calculation, the first step, what is the first step? You have to complete the first law. You need to label the current first. Okay, remember that. So we label the current. At the junction, we label at the junction, okay? So let's just call this current, okay, I3. This is I1. This is I2. Now, I pick the direction of the current. Because the battery here is positive, right? So I just take current coming out from here, go to the junction. Same here, positive, coming out from here, go to the junction. So they enter, and then I3 is this one. What about the current at point B? Same, this is I3. This one coming out is the same branch as I1. This is I1. And then here is I2. Okay, what is the first task? The first task is to distribute the current over in the entire circuit. You want to know how the current flow in the entire circuit. First is that, find out that one. Okay, so this is how I distribute. Now, after you have done the Kirchoff's first law, then to calculate the second law, you need to choose a calculation direction. Now, let me write it here. First is identify, distribute, I would say, distribute current direction. And then number 2, you want to identify calculation direction. Okay. Now, calculation is different. Current direction and calculation direction is different. First, you find the current direction, and then you find the calculation direction. Now, calculation direction is up to you. You want to choose. It's either clockwise or anti-clockwise. Because we have a loop. What is our loop? Focus on the upper part of the circuit. This is our loop. The direction of calculation, I can either go anti-clockwise or clockwise. Now, let's just pick one example that I choose to go clockwise. Okay, clockwise. So I start at whichever point I want. Let's say I start here. And then I'm going to go to the right first because I go clockwise direction. Okay, now remember, you need to have all the current label. Okay, so this is I1. That means the current flowing through here, I1, flowing through the cell is also I1. Yeah. Very simple, you use this method. First, we go to the right. Clockwise, am I right? So we go to the right. Now, look at the current direction. Label the point that is positive and negative. If you recall, how does current flow? They flow from high potential to low potential, correct? High potential, we put it as positive. Low potential, we put it as negative. So current always flow from high potential to low potential. So you want to label the plus and the minus at every single component. You see how I do it? This is the cell. Now the cell, this one is definitely positive lah. And then here is negative. We use the green. Okay, so here's not positive, here's negative. Now what about this R1? You see how the current is flowing. The current is flowing from right to left, right? So that means this side is positive, this side is negative. Okay, same for this one, the middle one. The I3 is flowing from left to right. So which one is positive? This is positive, this is negative. We always do positive to negative. So you need to use the direction of the current to label the sign. Okay. Now, after you're done labeling the sign, then we start our direction of calculation. We start here and we go clockwise, right? Now, remember this rule of thumb. Later, I will explain in a bit why we use this. But to simplify things, we follow the clockwise direction. You look at a sign where you're going from positive to negative. So that the first component is going to be a negative potential difference. So I will write here minus E1. I start with this one. You always look at the second sign. Okay, if it goes from positive to negative, then it's a negative potential difference. And then you continue to go. Okay, continue to go, follow the direction to the second component, right? So R1. You see the sign again, we're going from negative to positive. Negative to positive. So this is going to be a positive potential difference. So I will write here, continue here, positive. Okay, potential difference, that means is the current times the resistance, which is I1, R1. Okay, you see I1 is flowing through it, and the resistance is R1. So this is the V lah. This is the V. But I write it as positive I1 R1. Okay, because V equals to IR. And then I continue to go. Now, go down here. Is there any component? There's no component. Huh? So I go here. This component, R2. Okay, we are going from what to what? Negative to positive. Again, it is a positive potential difference. So positive. What is the current? Be careful the current, because the current flowing through R2 is I3, not I1 anymore. Okay, it's I3. So I write here potential difference VIR, so it's I3 and R2. Okay, and then continue to go. There's no component here, and we come back to our starting point. Then we finish our direction. We finish our loop, then I will write this equals to 0. This equation is derived from the Kirchoff's second law. It says the sum of the potential difference in one loop is equals to 0. Okay, so you need to be able to write this equation. In the exam, you will be asked to write the expression like that. Now, let me explain why this one we take negative, why some are negative and why some are positive. You see, let's focus on the first component. The first component like that. I take it out here. This is minus, this is positive, right? Why the first one is minus E1? You see, our calculation direction is going from left to right. Okay, I short it as direction of calculation, DOC, okay? Now, the way we calculate is actually like this. We take the 2 points between the component before V1 and after V2, okay? So when we calculate, we're actually calculating V2 minus V1 to get the potential difference. We always get this 2 minus 1, 2 minus 1. Okay? Now, if I ask you, which one is bigger, V1 or V2 is bigger? The potential. Do you think the positive side of the battery has a higher potential or the negative side? The positive side has higher potential, right? Because at the negative is already 0. So if I take V2 minus V1, you get a negative value. That's why you have a negative potential here, minus E1. Because V2 is bigger than V1. Okay? Now, if I see the second component, you see R1. Like that. Okay? Label the current also. The current is flowing to the left, I1. And then, where's our direction of calculation? We go to the right, right? DOC. So if I go to the right, then which one is my V1? This is my V1. This is my V2. Now, is V1 bigger or V2 bigger? Is the potential at point number 1 bigger or the potential at point number 2 bigger? You look at the current flow. Because this is not a battery, right? We cannot tell. A battery is very simple. You just positive must be bigger. But this is a resistor. So how do we know? We use the current direction. Current always flow from higher potential to lower potential. That means V2 is bigger than V1. V2 bigger than V1. Oh, sorry, this one I did a mistake, guys. This one is supposed to be V1 bigger than V2, right? This one. So that's why we get a negative. When we take V2 minus V1, we get a negative. Okay, now the resistor one, V2 is bigger than V1. So if I take V2 minus V1, I will get a positive value. So it's a positive potential difference. So what do I write here? What did I write here? It's a positive potential difference. So I write it positive I1 R1. Okay. Now, what about the resistor number 2? Okay, I draw it here. This is resistor number 2. Put the current in. Oops. I3 is to the right. Okay. Now, where is our direction of calculation? For the R2, we go clockwise, so that means this will be to the left. Okay, so going to the left, that means which one? This is my V1. This is my V2. If I want to get the potential difference, V2 minus V1. Okay, V2 minus V1, is it a positive value or is it a negative value? Again, you look at the current flow. Current always flow from high potential to low. So V2 must be bigger. When I minus it, I get also a positive value. So again, you have this plus the potential difference is I3 times into the resistance of the resistor here. So this is why we have this minus and positive and positive. Okay, so it's because of the which we always take V2 minus V1. And whether it's positive or negative, it depends on which side has a bigger potential. Okay, so that is the reason behind it. But when you do the question, you do not need to always think of this one, which one is bigger potential, which one is lower potential. That's going to be time consuming. So you use like the one that I mentioned. First, you label the current. And then what's the next step? You do the plus minus thing. Okay, plus minus thing. And then once you have the plus minus, you follow your direction of calculation. The sign always is the second one. So if you're going from plus minus, then that is a minus. If you go from minus to plus, then that is a plus. Okay, now I'll show you again. I'll show you one more example. Okay, so if you feel a bit confusing, not following, never mind. Here, I will show you more examples. Okay, I will show you many examples today. Let me just get some space. Okay, you want to capture, you capture first. Let's do another loop. We do like the loop at the bottom. Okay, we do the loop at the bottom. Clean up a bit. Okay, so we have our current labeled I3, I2, this one I2 here. Once you label the current at the junction, then you label everywhere, okay, everywhere, especially across the component. Okay, look at the loop number 2 at the bottom. Let's say I want to write an expression of Kirchoff's second law for loop number 2, okay? Loop 2, this is loop 1. Label my positive, negative. So I already have the current. Where is my positive, negative? Okay, following here, I3, I go to right. That means this is a positive. This is a negative, right? And then I go down here, I2 also flowing to the left. This must be positive, negative. Okay, use the current to help you. Current is flowing always from positive to negative. Now, when it comes to the cell E2, the cell, you just look at the terminal of the cell. This is negative. This is positive. Okay, and then you come back to point A. Okay, we already have the sign. Now, choose your direction of calculation. One important thing is that your direction of calculation cannot change. Once you choose one direction, you want to stick to it. The reason why many students, they cannot do the questions or they keep getting the wrong answer is because the direction of calculation, always they change it. You want to stick to it for the entire loop. Okay, choose one, whether you want to go clockwise or you want to go anti-clockwise. Now let's say I choose clockwise. Okay, I choose clockwise. So I'm going to write loop 2. I write it here, clockwise direction of calculation. Okay, pick one point to start. I start from point A. So I start going to the right, cross the R2. Is it a positive or negative potential difference? I go from positive to minus, right? So it's a minus. So I write here, minus. What is that? The current is what? Current is I3. So minus I3, R2. Okay. Continue, stick to the direction calculation. I go clockwise, so down here to R3. What sign do I go from? I go from positive sign to negative sign. Again, it is a negative. So minus I2. The current is not I3 already, it's I2. So I2 R3. And then continue to go to the E2. Look at the sign, it's a minus to positive. So it's a positive. Okay, positive. E2 is already the voltage, so I just write E2 here. Is there any other component? No more, right? So I continue here. I go back to starting point. So this becomes equals to 0. Like this. Maybe I can do a bit of arrangement. I put E2, move that one on the right hand side. So I3, R2 plus I2, R3. This is my answer. Okay. Same for the first one. I can also simplify the first one. This one I can write it as E1 equals to I1, R1 plus I3, R2. Here. From the Kirchoff's second law, equations, okay, E1, I1, R1, E2, I3, I2. And using these two equations, we can solve simultaneously to find I1, I2, and I3, which I will show you after this slide. Okay, we will look at one full example of how to solve using the Kirchoff's law. Okay, but this one is just to get to know the two laws, and then we will look at one example. Okay, 1 to 2 minutes, and then we go to the next slide. Okay. Example 1. A, find the current flowing through each resistor, and B, calculate the potential difference across each resistors. Okay, if you look at the circuit, it's considered a complex circuit. Okay, so we don't solve it using the Ohm's law, we solve it using Kirchoff's law. Now, first step, label the current. Okay, now how do I label the current? I can use the battery to help me. Okay, the cell here, negative, positive, so current must be coming out from here. I will call this I1, Same here, I1. And this battery, current coming out here, I2, I2, here, I2. Okay, now that means here is also I2, right? So I labeled on the branch because current in one branch is the same everywhere. So if this is I2, 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 and here is also I2. Now focus on the junction. The first junction, let's call this junction A. How many current coming in? I1 is going in the junction, and then I2 down here. I can label the current in this junction, current leaving junction I3. Now at first, you might get the current direction wrong, but that is okay. Because if the answer is not the direction you label, that means you will get a negative value for the answer. For example, if you label I3 is upward, and then when you do the calculation, you got a negative number. That means the real direction of the I3 is actually downward. Okay, so you know when you do the calculation, when you get a negative value, that means it is the opposite of whatever direction that you label. So it doesn't matter. It really doesn't matter at first the correct direction of the current. Most importantly is you want to distribute the current. Okay, you want to distribute the current. And when you distribute the current, of course, you want to check the junction. This one going in, 2 going out. What about here? This is I1, right? I1, and then I3 going in, I1 going in. Okay, now you check the current at the junction. At junction A, what is this? How do I write an expression? So current going in, I1, equals to current leaving. So I2 plus I3. Check at junction B. At B, can I write an expression? It's the same, right? I1 equals to I2 plus I3. So it's the same, then that means you have labeled correctly. Not the actual direction of the current, is the distribution, at least it is correct distribution. Okay, because we don't want current going in and like that. In one branch, like got two different directions. We don't want that. Okay, in any branch, there must be like one direction like that. Okay, so we are going to use this current direction to do our second law. Now, before we do the second law, remember we have to put in the sign first, right? The sign. So using the current that you label, you do the positive, negative. Okay, I3 going from here, current always go from positive to negative. Okay, high potential to low potential. Same here, I1 cross the battery. The battery, you just take the terminal, negative and positive. And the 20 ohm resistor is a positive here, it's a negative here. And then this one, negative, positive. I2 is flowing to the right. This is a positive. This is a negative. Okay, so once I have all the sign, then I can start my Kirchoff's second law. How do I start? Okay, we break it down into 2 loops. First loop, I take clockwise, this one. And then second loop is the bottom one, I take anti-clockwise like that. Doesn't matter clockwise or anti-clockwise, but I choose the one that align the most with the current direction. Okay, I choose it align the most because that is going to be easier. Okay, start somewhere. Loop number 1 first we do. Loop number 1, clockwise. Start from A, go to the first resistor, 10 ohm. Is it a negative or a positive? positive to minus, so it's a minus I3 times 10, so 10 I3. Okay, go to the next one, the 20-volt cell. So we go from negative to positive. It's a positive 20. Okay, remember must follow the clockwise direction. And then we go to the 20 ohm resistor. Positive to negative, so it's a negative 20 I1. Back to A, finish. So equals to 0. Okay, here I move everything to the right, so 10 I3 plus 20 I equals to 20. Maybe I can simplify 10, 1, 10, 2, 2. So 2, oops. I3 plus 2 I1 equals to 2. That become my equation 1. Put it aside first. Now we do a second loop, L2. L2, I go anti-clockwise. Okay, so anti-clockwise start somewhere. So I start from A, go down to the 40-volt minus to positive. So that's a positive 40. Okay, and then to the 10 ohm plus to minus, that is a minus. Current is I2, so 10 I2. And then go up to the 20-volt battery, negative to positive, it's a positive 20. And then we have a minus 20 I1 equals to 0, back to A. Okay, now 40 plus 20, 60. So we get this one is 10 I2 plus 20 I1 equals to 60. Okay, simplify. I2 plus 2 I1 equals to 6. Equation 2. Now from these two equations, I can solve simultaneous. But this is I3 and this is I1. This is I2 and this is I1. But I have this one, right? My Kirchoff's law. So I can express the 3 in terms of I1 and I2. Okay, so that means this one I can put it like I3 equals to I1 minus I2. Put it inside here, I get I1 minus I2 and plus 2 I1 equals to 2. So 3 I1 minus I2 equals to 2. Let's just call this equation 1. Okay. Now write it here, down here. Let me draw a line. 3 I1 minus I2 equals to 2. Then we have 2 I1 plus I2 equals to 6. 1, this is 2. Then I solve it. Eliminate the I2. So 1 plus 2. Equation 1 plus 2. We have 5 I1 equals to, this one cancel, 8. So this has become I1 equals to 8 over 5, 1.6 ampere. Now you get I1. After you get I1, then the rest you just put in the equation. So continue up here, I1 into equation 1, 3, 1.6, and then minus I2 equals to 2. Okay, we calculate this one. I2, we get 2.8 ampere. And then I3 is I1 minus I2. This is minus 1.2 ampere. Okay, now I already got my I1, I2, and I3. You look at I1 and I2, it's a positive value, right? That means I1 and I2 I labeled correctly in the circuit. Okay, the direction that I label is the actual direction. But if you look at I3 is a negative 1.2A, right? So I can change the direction here. Actually, this one is supposed to be pointing downward. Okay, you look at the I3, they are all clockwise, right? So now I change it to anti-clockwise. I3, 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 I3. So this is the actual direction. 1.2 ampere. So how does the current flow? Here, all right, already labeled on it. At first, when you look at the circuit, you don't know how the current flow. Okay, because if you try to find it by labeling, you will get a headache, because sometimes you have the battery like this, sometimes you have battery opposite to it. You don't know the current, whether it's going left or right. So at first, you always want to distribute first. Okay, it doesn't matter if it's actual or not. You want to distribute the current, and then you do the voltage second, the Kirchoff's second law, calculate the current. Then you know what is the real direction of the current. Now, once you have the current, then potential difference, then you just calculate that. So potential difference V 10 volt equals to I3 R 1.2 times 10. That's 12 volt. And potential difference for the 20 volt, 20 ohm, I1 R equals to I1 is 1.620, 32 volt, and potential difference for another 10 is I2R is 28. This one is for B. Okay. Okay, I'm gonna give you a 5-minute break, and then we come back. I have a set of exercises for you to do in class, and we will discuss some of the exercises also. But before that, we take a 5-minute break and we come back again at 8:05. Okay, we are back. Just 1 second. I'm sending the file. One to seven, guys. We have 7 questions. You try it out. And I will be behind the screen. If you have any question, if you need any help, let me know. There's a solution as well. when you do the calculation, right, usually the current is very small value. It can be up to 4 significant figures, very small value. So you want to be careful. Sometimes if your answer is not the same as the answer sheet, maybe it's because you didn't take all of the decimal places. So for example, if you get current equals to 0.0436476 then blah, blah, blah. When you write 4 significant figures, okay, 0.04377 is like how you represent your answer. But when you do the calculation, you want to take as many decimal as you can. Otherwise, your answer will slowly deviate from the actual answer. Okay. So in other words, because all the values are very small values, so it can be significant if you drop the decimal. So you want to take all the decimal. The difference can be significant. Sometimes the circuit, the current is already labeled for you, so you don't need to label yourself. Okay, like for example, 2B, the current is already labeled for you. You can use that current. If your battery has internal resistance, like 2A, you just expand the battery like that. This is R1, R2, and then this E2, right? It has got internal resistance R, right? So you can add like a small resistor at the side. Then you do this. Oops. This R. And then you do the voltage rule, same, treating the internal resistors as just like any other resistors. Okay, so the current is clockwise. So we choose our direction of calculation. We also choose clockwise. The signs plus minus, plus minus, plus minus, minus plus, and plus minus. Okay, then you get minus E2 minus IR minus IR2 plus E1 minus IR1. For question 3, you can write your circuit like this. Okay, so I will show you question 3. If you cannot do, you can look here. If you can do, you can just proceed with your question. Okay, question 3, we expand the battery. We draw in the internal resistor. And the ammeter also has a resistance, 5 ohm. So first step, we label current direction, distribute the current. So I use the battery to kind of give me an idea of how the current flow. So here, coming out here, and then they enter here. Okay, so this one I1, I2, and this one must be different. I call it I3. Okay, then using the first law, I3 equals to I1 plus I2. Then I label the sign. Okay, positive, negative. What about the 2 ohm resistor? Current is flowing like that, right? From right to left. So that means this is a positive, this is a negative. Same for this one, positive, negative. This is a positive, this is a negative. I can label the current over here as well. Like that. Ammeter also, you put here positive, here negative. Okay, so follow the direction that flow through the component. Now you get all the sign. Then we do loop 1, loop 2. Which one you want to take as your loop 1? I will take my loop 1 as like this, and I'll take my loop 2 like this. I just want to align as many as I can with the current direction. But if you do the opposite, no wrong, you will still get the same answer. Okay, loop 1. Start here. We go to the ammeter first. It's a negative 5I3. Okay, so negative potential difference. And then we go to negative 2I1. And then positive 3 equals 0. Rearrange. That become my first. Okay, loop 2. Let's start from here. So first is minus 5I3. And then minus 3I2, the internal resistance, and then plus the 2 volt. 0, 5I3 plus 3I2 equals to 2. That is my equation 2. Okay, our equation got I1, I2, I3, so you need to make it become 2 unknowns only. Okay, so that means I can change, okay, solving for I3. From equation 1. Okay, so I just sub the I3 equals to I1 plus I2 inside, so that I get an equation of 3 and I2, and then I can solve it simultaneously with the equation 2. Equation 2 also has got 3 and 2, I2. Okay, put it side by side, then you can solve it. Okay, that's for number 3.